Hi students, in this session we will discuss about the topics in module 3. First topic is stability and Routh-Hurwitz criterion. The definition for stability is that a system is stable if its output is bounded for any bounded input. That means for any finite input, the system output will be a finite output. So the system will be said to be stable. A system is unstable if for a bounded disturbing input signal the output is of infinite amplitude or oscillator. That means for a finite input, if the output is infinite amplitude, then the system will be unstable. That is the basic definition for stability and stable and unstable system. So first we will consider the impulse response of a system. Suppose if a system has an input C of t, it will produce as an output. Suppose if a system has an input R of t, then it will produce as an output C of t. And the system has got a transfer function. So in the case of finding the impulse response, we will give the impulse as input. That means R of t will be the impulse. Okay. So when R of t is impulse, that means input is input. The output of the system is called impulse response of the system. So for a impulse input, the impulse response of a system is the inverse Laplace transform of the system transfer function. That means we have given the system transfer function which is given as g of s, and then if you are giving an input impulse, that means R of t, and we will take the output as C of t, then C of t is called the impulse response, and that impulse response is obtained by taking the inverse Laplace transform of the system transfer function. So we can return the impulse response C of t will be equal to m of t into R of t, where R of t is the impulse and m of t is the system transfer function, that is time domain system transfer function. So it is obtained by, that means the response, impulse response is obtained by the convolution of the system transfer function and the input impulse. Okay. Bounded input. Next we will consider the bounded input, bounded output stability, that is called BIBO stability. BIBO means bounded input, bounded output stability. So the condition for, we will discuss the condition for BIBO stability. So if we are considering a relaxed system means that its initial conditions will be 0. So we will take the integration from 0 to infinity. That means below the range minus infinity to 0, the system output will be 0. That means initial conditions will be 0. So for the relaxed system, the response C of t, that means C of t is the m of t convolution R of t is the C of t. So for the relaxed system, the response C of t will be obtained by integral 0 to infinity m of tau into R of t minus tau into d tau. Actually this equation, integral 0 to infinity m of tau into R of t minus tau d tau, is the convolution equation. Basically we will take the convolution equation from minus infinity to plus infinity limit, but here it is given that we are considering the impulse response corresponding to the relaxed system. So we will take the integration from 0 to infinity. So this is the response equation for a relaxed system. So in the case of relaxed system, it is said to be BIBO stable, that is bounded input to bounded output stable. Then the condition is that its magnitude of the impulse response will be absolutely integrable. That means magnitude of the impulse response will be less than infinity, or it has got a finite value. So for the BIBO stability, for bounded out, it will produce a bounded output such that the condition is that integral 0 to infinity modulus of m of t d tau dt less than infinity. So this is the condition for BIBO stability. Okay. Next we will define the stability in terms of location of poles. If we are given the location of poles, then we can define the stability. So that we will discuss in this topic. Suppose the system transfer function is given as m of s. Here m of s is actually the g of s itself. Here the notation is taken as m of s. That means if you are giving the impulse as the input, then the impulse response will be m of s. Okay. Where the given that m of s is equal to b0 s raised to m plus etc. divided by a0 s raised to n plus a1 etc. And this is the form of the m of s, that is system transfer function. And that means system transfer function is in the form of a by b form, and here there is a numerator polynomial and denominator polynomial. Similarly, we can write the numerator polynomial as a product of the terms s plus z1, s plus z2, s plus z3 etc. up to s plus zm, and the denominator polynomial can be written as the product of the terms s plus p1 into s plus p2 etc. That means m of s can be written in these two forms. First is the polynomial representation, that one is the multiplied roots representation. And based on the location of the poles, here the zeros are z1, z2, z3 etc. up to zm, and poles are p1, p2, p3, pn etc. So the denominator term will represent the characteristic equation. That means the multiplication of s plus p1, s plus p2 into s plus p3 etc. up to s plus pn will be equal to 0. That is the characteristic equation. And for the first case, and the denominator side, that is a0 s raised to n plus a1 s raised to n minus 1 plus etc. will be equal to 0 is the characteristic equation. That is the denominator polynomial equate to 0 is the characteristic equation, and we can define the stability conditions as based on the location of the roots are, suppose if you are considering this term, that is s plus p1, s plus p2, s plus p3, s plus pn, then based on the location of roots, here the poles are, here the roots are s is equal to minus 1, minus p1, s is equal to minus p2, s is equal to minus p3 etc. up to s is equal to minus pn. So if the roots of the characteristic equation has negative real parts, then the system is stable. So that means if the roots of the equation has a negative real parts, then the system is stable. And if any roots of the characteristic equation has a positive real part, or if there is a repeated root on the imaginary axis, then the system is unstable. So if the roots such as p1, p2, p3 etc. has a positive real part, then it is a also then it has a repeated roots on the imaginary axis, then the system is said to be unstable. So third condition is that if the condition 1 is satisfied except for the presence of one or more repeated roots on the imaginary axis, then the system is limitedly stable or marginally stable. So the condition is that if the condition 1 is satisfied, that means the roots of the characteristic equation has a negative real parts, but some of the roots have repeated roots on the imaginary axis, and then the system is said to be limitedly or marginally stable. So these are the condition for stability when we are considering the roots of the characteristic equation. So the location of the roots is given. So we are actually representing this in terms of S-plane, right? S-plane means that there will be a y-axis and also there will be a x-axis, and x-axis is considered to be the real axis and y-axis is considered to be the imaginary axis. So location of the roots will give the measure for the stability. Suppose we have a real axis as x-axis and imaginary axis y-axis. If the roots have negative real parts, means that it will lie on the negative x-axis. Okay, and in such condition the system will be stable. If the roots of the characteristic equation has a positive real part, or if there is a repeated roots on the imaginary axis, then the system is unstable. Suppose the roots are lying on the imaginary axis, that means on the y-axis, or roots are lying on the positive real axis, that means positive real axis means that positive x-axis, then that system is unstable. So if the location of the roots is on the positive x-axis or on the imaginary axis, then the system is unstable. Suppose if some of the roots are lying on the imaginary axis and some are lying on the negative real axis, then the system is marginally stable. So this is the condition for stability. Okay. And next condition, stability conditions based on the coefficients of characteristic polynomials. Suppose now you have defined the stability condition based on the location of roots on the real and imaginary axis. Now if you are considering the characteristic equation as this polynomial, that is a0 s raised to n plus a1 s raised to n minus 1 plus a2 s raised to n minus 2 plus etc. will be equal to 0, that is a polynomial. In such case, this we can define the stability based on the coefficients of this polynomial, where the coefficients are a0, a1, a2 etc. up to an. We will look at the coefficient and we will define the stability. Okay, so the condition for this stability is if all the coefficients are positive and if no coefficients is 0, then all the roots are in the left half of the S-plane. So we will mark the roots on the S-plane, where S-plane is composed of a real axis along the x-axis and an imaginary axis on the y-axis. So if all the coefficients are positive and there is no coefficients with 0, then all the roots are in the left half of the S-plane. That means if this condition is satisfied, that means all the roots will be on the left of the S-plane. That means left of the S-plane means if you have a y-axis like this, that means imaginary axis like this, left side is this side. Okay. So if you are drawing a y-axis, like this, then the left side will be this side. Okay. So if all the coefficients are positive and if no coefficient is 0, then the roots are lying on the left half of the S-plane. And the next condition is if any coefficient ai is equal to 0, then some of the roots may be on the imaginary axis or on the right half of the S-plane. Suppose we have a characteristic equation like this. If any of this coefficient is 0, that means that term will be absent here. So if any of this coefficient will be 0, then the roots will lie on the right half of the imaginary plane. That means if the imaginary axis is like this, then the roots will lie on the right half of this plane or on the imaginary axis. That is the second condition for stability. Imaginary axis. Okay. So if the roots are lying on the right half of the plane, that means it is unstable. Or if the next condition is that if any coefficient ai is negative, then at least one root is in the right half of S-plane. Suppose if any of the coefficients suppose in this equation, if any of the coefficient is negative, then the roots will lie on the left half of the S-plane. So if the root is lying on the left half of the S-plane, that means then the root will be lying on the right half of the S-plane. So the system will be unstable. That means if any of the roots is lying on the right half of the S-plane, that means the system is unstable. So this is the basic condition this is the necessary condition for stability. So this is a condition sufficient necessary. This is a condition, but it is not the sufficient condition for stability. So based on the coefficients also we can predict the stability, but it is not the sufficient condition for stability. That means if roots with the negative real parts, that means if the roots are negative, have a negative real parts, that means the system is stable. And this means that the quotient polynomial, all the quotients will be positive, then the system will be stable. So this is the necessary condition and sufficient condition for the stability. So if the quotients, all the quotients are positive, then then the system will be stable, but it is a necessary condition, but it is not sufficient to predict stability. So if all the quotients are positive, then we have to check for roots with negative real parts. If all the quotients are positive and roots with negative real parts, then only we can say that the system is completely stable. So if you are given that the quotients are positive, then you cannot predict that it will be a stable system. So we have to check for whether the roots have negative real parts or not. So this is the necessary and this is a sufficient condition for checking the stability. So if all the roots have negative real parts, then we can say that the system is completely stable. That means that if the roots have negative real parts, then it indirectly indicates that the quotients will be positive. So this condition will be always true, and this is the condition for stability, and backward condition is not always true. Okay. So if all the quotients are positive, you cannot predict that the roots have negative real parts. So you cannot say that the system is stable if it is given. Okay. So if it is given, you have to check for this condition also. So there is a criterion which is called Hurwitz criterion, and actually this criterion gives the procedure for determining whether the roots of a polynomial have a negative real part or not. So Hurwitz criterion is the checking, it is a procedure for checking the stability of the system, and actually what Hurwitz criterion is doing is that it will check whether the roots of the polynomial have negative real part or not. That means in the polynomial, if you are giving the question, you will given the polynomial such that a0 is raised to n, etc. And if you are find that its quotients are positive, that means a0, a1, etc. up to an are positive, then you cannot predict that the system is stable. Then by using the Hurwitz criteria, you can check whether the system is stable or not. And